All right, today we're going to talk about matrices and linear transformations. Before we talk about what a matrix is, let's just do a quick refresher on what linear transformations are. So on the right, we have what linear transformations might look like geometrically. And typically they're going to be rotations or stretches or shears or reflections or combinations of these things. So every time you think of a linear transformation, you should think of, something getting stretched and pulled, maybe shrunk down or rotated, or doing some combination of them. But the question we really want to ask today is, how the heck do we compute these linear transformations? Computers or your calculator or even yourself aren't necessarily going to crunch the numbers geometrically. We have to crunch them using algebra and arithmetic. So with that, let's remember what a transformation has to look like algebraically. So last time we learned that you're not allowed to have anything that looks funny. You're not allowed to have an x squared. You aren't allowed to have a sine x. You aren't allowed to have an ln y. The formulas of linear transformations have to look very pure. And in fact, the only thing you're allowed to have are x's and y's or z's or whatever your inputs are, and coefficients of those. Right? These are the only wildcards, these boxes right here. These are the only choices you have when making up a transformation. So let's go ahead and kind of see what this looks like in one dimension. So remember that if you have a function that goes from R1 to R1, that means we have one input and one output. So if you have a linear transformation, that's going to look like something like f equals mx. Now, just as a reminder, for our purposes, there's not even a plus b. So if you're wondering where that plus b is, we require that f of 0 is 0, that the y-intercept in some sense is always going to be 0. We're going to come back to that much later. So for our purposes, the only thing that you can change, the only dial you can move for a linear transformation in one dimension is this m, which is a number, which you might remember as the slope. All right, so what about R2 to R2? So R2 to R2, we have one input and, two inputs and two outputs. And what would that transformation look like? Well, more specifically from what we did before, you have some choices. You can multiply something times x plus something times y for the first output. And for the second output, you have a similar choice, but you can choose different numbers. So you might end up with something like this. Now this looks very weird, right? This looks like a big mess of variables, but keep in mind, this is still very constrained for all the different possible functions you might have from R2 to R2. Right? All the different functions might have squares and square roots and e to the x and ln of y's, but for a linear transformation, it boils down to this. And what we want to do is come up with an easier way to think about these types of transformations. So what we're going to do is we're going to encode these coefficients into a matrix. So we're going to encode these guys into a matrix. And this might seem random. Why would I just do this? But keep in mind that if I give you this matrix, if you're told what this matrix is with just these numbers, you can go back to this setup right here and fill in the x's and the y's and compute the transformation. So these coefficients, these m's, are enough to figure out what the transformation is. Right. So that matrix is going to define the transformation. Let's go up one more level. Let's go from R2 to R3. So this R2 to R3 means we have two inputs and three outputs. So we might have a function that looks like this. We're going to have two inputs, and now we're going to have many more outputs, and we're going to have something that looks similar, but one of the main differences is we're going to have an additional row. Oops, that's not right. So it's going to look like that, and we can take all of these coefficients right here, and and we can too encode them into a matrix. And while we're getting rid of the x's and the y's, if I give you this matrix, if you're told what this matrix is, that's enough to go backwards and figure out what the formula for the transformation is. But what's really cool and really beautiful is that we can actually make this, all these equations look more like this simple f equals mx. This m will be the slope. And in fact, what we're going to do is we're going to write this transformation. We can write this very transformation, or what we want to do, which I'm going to show you how to do, is we're going to write it like this. This matrix right here is going to be this big M. So instead of having a single slope, in some sense, you're having a whole array, a whole matrix of slopes. And you're going to multiply it times this vector, and this defines a linear transformation. So the key point to get across, every linear transformation is encoded by a matrix. And vice versa. So every time you kind of see a linear transformation, you should think that's just a matrix. And moreover, every time you see a matrix, you should say that's just a linear transformation. These are one and the same. They're just different ways of thinking of the same thing. And the only question we have to answer is how the heck do we multiply these things? Right? This is kind of a mystery. I kind of motivated it with it and told you you could multiply these. How do you do this? So let's go ahead and do that with an actual example. Right. Right. So this is a matrix. I should mention this matrix has 3 rows and it has 2 columns. So this is going to be, this matrix is going to encode a function which goes from R2 to R3. Right, so the number of rows, this one right here, this one is encoding the number of outputs. So that means when we multiply by a vector, what's going to come out is a 3-dimensional thing. There's going to be 3 numbers here. Right, so the rows are always going to be the same. What's a little weird is that the number of columns on the inside on the matrix has to equal the number of rows over here. So this one has 2 rows. In fact, you can think of this matrix as a 3 by 2 matrix because it has 3 rows and 2 columns. And you can think of this vector in a very similar way. It's a vector, it's a 2-dimensional vector, but you can think of it as a 2 by 1 matrix. Right? You can think of this vector as a 2 by 1 matrix. And you'll notice this is kind of weird, and this seems magical, but you'll notice that these 2 on the inside have to match. And when they go away, what do we get on the outside? We're going to get a 3 by 1 matrix or a 3D vector. And sure enough, that's exactly what we want because this matrix right here is going to encode a function that outputs something in R3. So what we get out should be a 3-dimensional vector. So let's go ahead. I'm going to rewrite this. And we'll go through how to do this. So we know we're going to get out 3 things. So let's just do the first one. So for the first one, what we're going to do is we're going to multiply those 2 together, 1 times 1. And then we're going to add what happens when we multiply the next two. So we're going to add -1 times 2. And then we're going to do the same thing again for the next one. For the next row, what are we going to do? We're going to do the same thing. We're going to take the first row, we're going to go the rows, and we're going to do the first entry in the second row times the first entry in the vector is going to be 3 times 1. And then we're going to take the second one, so plus 2 times 2. And then finally, I already used orange. We're going to do this again. 0 times 1 plus -2 times 2. Right? So it's not a coincidence that these ones are all the same as this one right here. And additionally, it's not a coincidence that these 2's are all right here. And it's also not a coincidence that you'll notice that, in fact, this entry right here is in fact there. In fact, if you get rid of the blue and the yellow highlight, you're left with exactly what the matrix is. All right, so let's see what this does. What does this do? This gives us just a single vector. We just go through the arithmetic and just do it. So we should end with -1, 7, and -4. All right, so that is this product of this matrix times this vector. Okay, let's go and just do a simpler example. Just do a 2 by 2. So this 2 by 2, we're going to have the same number of rows, right? The number of rows has to match on the output, and the columns, the number of columns has to match the inside over here. So this, just to get into a habit, this is a 2 by 2, and this vector is really just a 2 by 1. These are going to cancel right here. So we're going to end up with a 2 by 1. Right, so what we're going to do is we're going to take this first column and we're going to multiply it by those values in order. So we get 1 times 2. Whoops, that's not good. We get 1 times 2 plus -1 times 3. And then we're going to get 0 times 2 plus 4 times 3. And so altogether, we're going to get -1 and 12. Right, so this is kind of just something to practice. It's a little weird. It seems weird. In just a second, I'm going to kind of knock some more sense into it. Why does this work? Why is this a linear transformation? But this is how these linear transformations are calculated, using these matrix vector multiplication. Before I continue, let's go over some properties of matrices and vectors. So these are things that you should keep in mind. I bring this up not because these are things you should already know, but some of the things that you would find intuitive going forward are actually not going to be true. So it's important just to keep in mind whenever we introduce a new concept, just to do a double check, do all the things that you'd want to do algebraically. If you want to factor or multiply or distribute or commute things, is that work? So certain properties of matrices and vectors. So one of them, which is important, is that you can add two matrices together if they're the same size. So for example, you can take a matrix like this. Oops, that's a 1. And I can add it to another matrix. And this happens, you do this in exactly the predictable way. You're just going to just add up the two entries. So this would just be you just add up these two, and then you're going to add up the next two, and the next, kind of fit. All right. Other things that are pretty cool is that if you multiply across a vector like this, this is the same thing as doing it individually. So this is something you can do. You're allowed to break this up and apply the matrix multiplication. This is distributing. You're allowed to do this. And similarly, if I have a matrix A times two vectors, like that, if I have a sum of two vectors, you can additionally break this up just like you'd predict. Right? So in a literal sense, a matrix is just like a multiplier in one dimension, and the only difference is it kind of acts in this weird way. Right? So these are kind of important things you can do. To kind of knock some sense into why does this encode linear transformations, let's just do one more example of before and after maps. So let's take a transformation, and we're going to define this transformation to be A, this is a matrix, times our vector xy. Right? Or even going forward, we actually may write it like this. Just pretty simple. But let's take A to be the matrix 2, 1, 0, and 1. Right, so that's going to be our matrix. And what I want to do is do the before and after map. I want to convince you that this matrix, even though it's not on its surface a simple rotation or shear or reflection or stretch, it is a function that obeys the idea that it takes lines and lines. It's not doing anything too fancy. And when you see the picture, it'll be convincing. So let's just do the picture. So let's take some vectors. And let's do one more. Here we go. And keep in mind, all of these lie on some circle. Okay, kind of, maybe didn't draw the best circle, but there we go. And we want to find, okay, what happens to all of these vectors? So this first vector right here is 1, 0. So what we want to do is we want to apply, we want to figure out what is 2, 1, 1, 0, 1 times 1, 0. Right? So if we do that out, that's going to be 2 times 1 plus 1 times 0, and 0 times 1 plus 1 times 0. There we go. Okay. Something's not right. Oh, that's right. Okay. So we get, if we do this out, we're going to get 2, 0. All right. So here we have the green vector is going to go to 2, 0. All right. We can do the blue one. The blue one is 0, 1. Where's that one going to get mapped to? That's going to be 2, 1, 0, 1 times 0, 1. And we're going to get 2 times 0 plus 1 times 1, and 0 times 0 plus 1 times 1. And we get out 1, 1. So we get out this vector right here. So if we wanted to, we could go do all the other ones. So we're going to get something that looks like this. Sorry. And then also something that looks like this. I'm not going to do it algebraically. You can do it if you want. And you can see that you kind of get this nice little shape like this. And the lines correspond to lines. So again, nothing fancy is happening. If I take the vector, let's just try this. If I take the vector 0, 2, so I'm going to take the vector that's twice the blue vector. Right? What's going to happen here? If we apply the transformation, what do we get? We get 2 times 0 plus 1 times 2, 0 times 0 plus 1 times 2. And sure enough, we get 2, 2, which is exactly twice here. So one property of linear transformations has to be that if you stretch the input by a certain amount, the output also is stretched by exactly the same factor. The only thing that really matters about linear transformations is the direction. Right? The length affects the length on the outside, but in the end, it's the same scale. So it does, as long as you just know what happens in each direction, that's good enough. And you'll see that this is going to hold for all of these. And this is true for any matrix. So going back to one of the properties, one property we can add to this is that I take a matrix and I multiply it by k times the vector. That's the same thing as k times a times the vector. So you'll notice that these two should look eerily familiar. These two just say in plain language that you can apply the vector before you add them together or after you add them together. That's the first one. This is property 1 from last time. And this one is also property 2 from last time. So the matrix is precisely encoding the linear transformation. Right. So that's it for this time. So the main skills for this time is just to get used to this matrix. What is a matrix? Can you multiply them together? Can you see that it's a linear transformation? That's really what I want you to get out of today. Over the next couple of sessions, we're going to focus a lot on exactly how to do these guys. So each of these has a matrix associated to them. And what we're going to do over the next couple of sessions is try to figure out what are each of these individual matrices, so you have a better understanding of really what's going on underneath all of this algebra.